Hello, my name is Edward C. James, and I'm a student at Dakota State University. And this is my final presentation for my INFA 725 Hacking the Art of Exploitation, and I'm doing the networking portion of it. First, I'm going to start out by presenting an important portion of networking, and that is a structural language of computer communications that is described in the layers of the OSI model. There are 7 different layers, and I'm going to be describing every single one of them. Layer 1 is the physical layer. This is a physical connection between 2 points. Rapid streams pass across this layer. Layer 2 is the data link layer. This layer deals with actually transferring the data between 2 points, and this is where data activation, maintenance, deactivation, error correction, and flow control take place. Layer 3 is the network layer. This layer passes information between the lower and the higher layers. Addressing and routing takes place here. Layer 4 is the transport layer. This layer provides transparent transfer of data between 2 systems. This is where reliability takes place. Layer 5 is the session layer. This layer is responsible for establishing and maintaining connections between network applications. Layer 6 is the presentation layer. This layer presents the data to applications in syntax they understand. This is where encryption and data compression take place. Layer 7 is the application layer. This layer keeps track of requirements of the application. Data encapsulation and sockets. Now that every time data passes through every layer, it becomes encapsulated into a layer for every layer of the OSI model that passes down from the application to the physical layer. Once it reaches the other side, it becomes decapsulated as it passes up from the physical all the way up to the application layer. Sockets are designed to send or receive data over networks. It is transmitted via the session and transport layer. The most common type of sockets are stream and datagram sockets. Stream sockets are reliable and verified form of communication. These sockets utilize the transport control protocol, which exists at the transport layer. This is useful when communication must be verified and transferred without excuses, even at the expense of speed and time. The datagram socket sends the data as a best effort and in an unreliable format. It doesn't mean that it's not going to get there, but it's that these sockets utilize the user datagram protocol, which also resides in the transport layer. This is useful when data must be sent fast and in a timely manner. Even if some packets are lost, such in the case of voice or video, which is important for them to get there, rather than which is important for them to get there in a timely manner, so that the voice can be understood or the video can be viewed. Packet addressing and port communications. Addressing of packets takes place at the Internet Protocol layer, and it is broken down into 4 chunks of 8 bits. This is utilized for routing purposes, so the packets become delivered to the right host. Ports are utilized so that addressing can be delivered to a specific transport layer communication entrance. Such entrance is in the form of TCP or UDP for sending and and delivering the data addressed by the network layer. Now, as far as addressing and port selection examples, a good example will be telnet connection to an IP address. The network protocol determines where such connection is to be sent via the addressing and establishes the entrance with the port. For example, the address might be 192.168.1.10, and in the case of the telnet connection, it'll be via port 23, utilizing a reliable connection via TCP. Now, HTTP connections via web browser. HTTP may be more involved because it may include other ports associated with the transport layer protocol. HTTP is the port to communicate via web browsers and other applications that may involve using hypertext transfer via port TCP number 80. When utilizing a web browser, a name resolution rather than addressing may be used via the DNS, which is utilizing TCP port 53 for some transfers, and queries are usually done on UDP. Um, Other applications such as FTP and TCP port 21 may be associated with the web browser integration, making HTTP one of the most used and complex protocols involved. Now, web server response and the OSI model. A web server accepts a TCP/IP connection via port 80 for HTTP protocol. Once that takes place, further layers of communication are implemented. Connecting handling code is separated into functions such as get and head that will retrieve a response. If such request isn't found, usually a 404 HTTP, which is not available, is the response retrieved. When using a web browser, all 7 layers of the OSI model are taken care of for us. Layers 7 and 6 are in the plain text, since all other details of the connections are taken care of at the lower layers. Sockets exist at layer 5 to provide interface to send data from one host to another. TCP exists at layer 4 to provide reliability and transport control. IP exists at the network layer to provide addressing and packet level communications. Ethernet exists at layer 2 to provide address between Ethernet port via MAC addressing, and wire communication exists at layer 1 to simply send the bits over the wire from one device to another. Now, MAC address communication versus IP address communication. MAC address communication exists at data link. It's a standard for media access control address, and it is a physical address as if it was the address of a house. On the other hand, IP addressing is a logical address as if it was a telephone number. Just as a phone number, it can be changed, but a house number cannot, unless it's a mobile house, but then we're talking about a whole different idea here. An IP address may be changed, but not a MAC address, at least not without implementing spoofing, which I will talk about it later. An IP address is composed of 4 8-bit octets or spaces. It is denoted in decimal numbers, but it is read by the computer in binary. A MAC address is composed of 6 bytes and it is composed of hexadecimal values. The addressing may be picked from 0 to F on every byte, but then the computer again translates it to a binary in order to identify it. Now, IP address and MAC address correlation. How are they related? The correlation between MAC addressing and IP address is translated by the address resolution protocol. In the local area network, MAC addressing is relevant to the communication of 2 computerized units. Therefore, IP addressing must be translated to MAC addressing. A broadcast is sent to every unit in the local area network in hopes that one MAC address claims the IP address that wants to be contacted. For example, unit with a MAC address with an IP address of 10.1.1.1 with a MAC address of all zeros and then all A's at the end, desire to contact unit with an IP address of 10.1.1.4 with a MAC address of all zeros and then all D's at the end, within a 4-unit local area network connected to which in turn is connected in a hub environment. Basically, the sending computer will obviously ignore its own message since it doesn't belong to it. The computer with the IP address 10.1.1.2 and MAC address of half zeros and half B's will ignore the message. Computers with the IP address 10.1.1.3 and the MAC address of half zeros half C's will do the same thing, will ignore the message because it doesn't belong to it. And the computer with the IP address 1.1.1.4 and MAC address half zeros half C's will reply with a message just stating, "Hey, I'm here. That's my address." Now, IP address communication. Communication between units, such as address, is composed of a portion preset for host usage and portion preset for network usage. Now, the first portion of it is allocated for the network usage, and the second portion is going to be allocated for the host usage. This is done in the following manner for Class A networks. For example, the first in a Class A network, matter for that one is wrong. I put that one for Class A, and it's actually Class E because that one was wrong. So this is for a Class C network. That was my mistake right there. It's actually be network, and the last part host. In the class of an A class, in the case of a Class A network, it'll be network, host. but that was my mistake. IP addressing has the following accommodations based on the size it needs. Class A ranges from 0 to 127 on the first octet, and it's actually network host. I had it wrong here again, so it's host You can allocate 127 separate networks and 16,777,216 host addresses. Class B ranges from 128 to 191 on the first octet, and it's network host. Can allocate 16,384 separate networks and 65,536 host addresses. Class C ranges from 192 to 223 on the first octet, and it's actually, this is the one that I had wrong as well. It's actually network host. You can allocate 2,097,152 separate networks and 256 host addresses. Now, IP and ICMP. The Internet Protocol is mostly used to transmit packets wrapped in a higher layer. The IP contains a header which utilizes checksum in order to detect transmission errors and fields that deal with packet fragmentation. ICMP packets are used for messaging and diagnostics. It is used in cases where connectivity wants to be tested. ICMP echo request and echo reply messages are used by a utility called ping. If one host wants to test whether it can be route traffic to another host, it pings the remote host by sending an ICMP echo request. Upon receipt of the ICMP echo request, the remote host sends back an ICMP echo reply. The transport layer. Now the transport layer is in charge of maintaining connections and ensure delivery of the two major protocols at this layer are the TCP and UDP protocols. TCP is the most common of the two and is used by Telnet, HTTP, SMTP, and FTP, and many more. This is due to the fact that it provides a transparent and reliable bidirectional connection between the two IP addresses. Now, reliability means that TCP will ensure that all of the data with all the data will reach its destination in the proper order. If the packets of the connection get jumbled up and arrive out of order, TCP will make sure that they are put back in order before handling the data up to the next layer. The functionality of reliability is possible by the set of flags called TCP flags and by tracking values called sequence numbers. Now, such flags are urgent, which identifies important data; acknowledgement, which acknowledges the packet; push, which tells the receiver to push the data through instead of buffering it. Now, reset resets the connection. Synchronize synchronizes sequence numbers at the beginning of connection, and finish gracefully closes the connection when both sides say goodbye, basically. Sequence numbers and acknowledgement numbers are used to maintain state. The sync and acknowledgement flags are used together to open a connection in 3 steps handshaking process. When a client wants to open a connection with a server, a packet with a sync flag but an acknowledgement flag is sent to the server. The server then responds with a packet that has both the sync and acknowledgement flag turned on. This is to complete the connection. The client sends back a packet with the sync flag off but the acknowledgement flag on. After that, every packet in the connection will have the acknowledgement flag turned on and the sync flag turned off. Only the first 2 packets of the connection have the sync flag on, since those packets are used to synchronize sequence numbers. Sequence numbers allow TCP to put unordered packets back into order to determine whether packets are missing and to prevent mixing up packets from other connections. Now, connections and sequence and constant contrast of UDP. When a connection is initiated, each side generates an initial sequence number. This number is communicated to the other side of the first 2 sync packets of the connection handshake. Then each packet that is sent, the sequence number is incremented by the number of bytes found in the data portion of the packet. Now, this sequence number is included in the TCP packet header. In addition, each TCP header has an acknowledgement number, which is simply the other side's sequence number plus 1. And now, as far as the contrast of UDP, UDP has much less overhead and built-in functionality than TCP. Its lack of functionality makes it behave much like the IP protocol. It is connectionless and unreliable, without built-in functionality to create connections and maintain reliability. UDP is an alternative that makes the application to deal with these issues. The UDP header contains only four 16-bit values in its order, which is source port, destination port, length, and checksum. Now, now I'm going to talk about network sniffing and spoofing. On the data link layer lies the distinction between switched and unswitched networks. An unswitched network, Ethernet packets pass through every device on the network, expecting each system device to look only at packets sent to its destination address. However, it is fairly trivial to set a device to a promiscuous mode, which causes it to look at all packets regardless of the destination address. And as far as spoofing, it is the art of forging addresses in a packet. The addition of spoofing to your bag of tricks greatly increases the number of possible hacks, since most systems are expecting a source address to be valid. Now, denial of service. Instead of trying to steal information, a denial of service attack simply prevents access to a service or resource. There are two general forms of denial of service attacks: those that crash the service and those that flood the service. Now, denial of service attacks that crash the service are often dependent on poor implementation by a specific vector. This is with the intention of crashing the system so that no access may be available during the denial of service. A flooded service is a service that has been exhausted and its connections are not available anymore. Even though it's still running on the background, it is still inaccessible, since all connections have been established already with the denial of service attack. Now, the ping of the death and the distributive denial of service flooding. Let's see what they are. According to the specification for ICMP echo messages can only receive 65,536 bytes of data in the data part of the packets. When there's an excess of these messages, the system becomes flooded and therefore inaccessible for since the service become denied and unable to respond. A distributed denial service is basically a distributed version of a floating denial service attack. In the distributed denial service attack, the attacker first compromises a number of other hosts and installs daemons on them. These hosts are sometimes called zombies as well. Systems installed with such software, they're the zombies or bots, like I said, and they just wait patiently. They sit idle until the attacker picks a victim, and then at that point he utilizes the bots or zombies to perform the attack. Once they perform the attack, that's when the denial service occurs. And that was my presentation for the INFA 725 Advanced Network Hacking. I will be coming up next with a few labs, follow up by a lab that I will design and have you guys do it, and then finally I will give the answer of how to perform the final lab. Thank you. Have a great day.